Imagine you are a chef and today you want to make pizza. You have a lot of tasks for that. Knead the dough, cut the vegetables for toppings, prepare the sauce. At the end, clean the dishes. If you work on it alone, that would take a lot of time because you need to do one after the other. But while you knead the dough, can somebody else prepare the sauce? That is a completely separate task and has nothing to do with the dough at this point. Similarly, another person can cut the vegetables. So once all these independent tasks are done, then finally you can put all these things together to bake the pizza. This way, a lot of time could be saved when multiple people handle independent tasks. This is exactly the idea behind multithreading. We all know the main thing in a computer is the CPU, which executes the instructions in a program. Inside CPU, we have cores, which are independent processing units responsible for reading instructions and executing calculations. Programs are the set of instructions run by the CPU. A browser, for example, is a program. The different softwares we use in our computer are also programs. When the program runs, the operating system creates a process to manage its execution. Process is basically an instance of a program that is being executed. So when we open a browser, that becomes a process in the operating system. And in this process, the smallest unit of execution is called a thread. A process can have multiple threads that runs independently. In browser process, multiple tabs can run in independent threads. Rust uses multithreading to achieve concurrency. Most languages suffer from one or more of these problems. Rust eliminates an entire category of bugs at compile time. The ownership system and borrow checker works together to make concurrency much safer. This is why Rust calls it Fearless Concurrency. Let's look at how we can create threads. Firstly, to use thread, we need to import the thread module. Inside main, we can create a variable t and we can create and assign a thread. Thread can be created by using the spawn method. This spawn method accepts a closure as an argument, and this closure has to implement the trait fn once. So the closure can be executed only once. Inside this closure, whatever we will write will be executed in a separate thread. And at the end, we can print something to show that the execution is finished. If we try to run this piece of code, we will see the final message getting printed, but the message inside the thread may or may not get printed. Obviously, the question arises that why is this behavior so unstable? The reason is that when Rust compiler starts a program from the main function itself runs in a thread, often regarded as the main thread. This main thread does not wait for anything. So when we spawn a thread from inside this main function, if that new thread takes more time to execute than the main thread, then we never see the print line declared inside the thread. So to let this spawned thread complete its execution, we need to make this main thread wait. How do we do that? By using the JoinHandle. We saw this spawned method accepts a closure and it returns a JoinHandle. JoinHandle is a struct that represents a handle to the spawned thread. It basically gives you means to control the thread, allowing you to join or wait for that thread to finish and retrieve its return value. So this t returns a JoinHandle, which has a method called join, and it will take ownership of the handle and makes the main thread wait and returns a result enum. So we can use unwrap to get the result. Now if we run it, every time this thread will finish executing and then the main function will end. When we try to achieve concurrency, we definitely won't be having just one thread with so simple of an operation. So we can have a thread which will print something in loop. And after printing, we can make the thread sleep for some time. I'm keeping sleep time 10 milliseconds for now. Since we are using duration, we need to import the module. We can now replicate the same thread one more time. And we'll make both of them join to the main thread. And run. So in this execution, sometimes T1 runs first and sometimes T2. This shows that both are getting executed independently. We can modify the print statements to print the thread ID as well. Same for the other thread. This current method returns the current thread and we are getting ID of that thread to print. We'll run it. This thread 1 represents the thread ID 2 and thread 2 has the ID 3. So we can see ID 2 and ID 3. Can you guess where is the ID 1? That's the main thread. If we get that thread ID here in main and run it again, now you can see that thread ID 1 is for the main function. Coming back to the first example, if we have a string and try to access it inside the closure, usually it works. We know closures can reach the variables from its environment. But if we run this, we get the error that closure may outlive the current function, but it borrows s, which is owned by the current function. This is what I was explaining earlier, that the main function can complete the execution before the closure running in the thread. So in this case, we need to transfer the ownership to the closure. We already know how to do that. We can do it using the move keyword. Now if we run it, it will work fine. You need to understand here what spawn method is doing. This is a representation of the spawn method signature. It has two generic types, F and T. F represents three things. Firstly, it's a closure and implements the trait fn once. Secondly, this F type should implement the send trait. Send denotes a type to be safe to transfer ownership across threads. So when we say something is thread safe, that means it is marked by the send trait. Also, send is an auto trait, also called marker trait, which means the Rust compiler automatically implements the send for your custom types if all of its fields and component types also implement send. We previously saw in our box pointer video that RC smart pointer, which is not thread safe, whereas ARC is a thread safe smart pointer. Finally, the static lifetime constraint. This is a very important one. It means that the closure and any data it captures must be able to live for the entire duration of the program. So what is the significance for this? We just now saw this example. When we didn't use the move keyword, we got the error closure may outlive the current function. That's the reason why everything a thread gets should have a static lifetime. Then again, we only had one thread. What if we have multiple threads which wants the string? If we write this way, it won't work because s has already moved inside the first thread. So you can't move it again for the second thread. Also, we saw immutable reference won't work. So what can be done here? This is where ARC smart pointer comes into the picture. We can use it here in this program. Before we use ARC, let's first understand how it works. ARC stands for Atomic Reference Counter. Atomic because the operations are indivisible tasks that either completes entirely or fails completely. Other parts of your program can never see it in a half-finished state or interrupt it in the middle. That's why it is thread safe. And reference counter is because since this is a smart pointer, when it is created, the data gets stored in the heap, but alongside it, there is another value stored for reference counter, which will have the value 1. Because at this point, this data is referenced by one variable, which is this original variable. We can now create as many clones of this original variable, which won't create the data again in the heap. Instead, we'll refer this existing heap location and will increase the reference counter. A quick note here, actually this reference counter is called a strong reference counter because there is another weak reference counter. The weak reference counter is used to prevent memory leaks caused by the circular references, while safely allowing non-owning access to the data, like a parent struct referring child struct and the child struct is referring parent struct. So to break this cycle, we can use a weak reference and then initially create the parent without a child using the new cyclic method of ARC to handle the mutual references safely. Now coming back to our example, we can first import and then create this string using the ARC smart pointer. We can then create two more references for two threads. We can either just use the clone method on the s variable or can use the clone method of ARC and pass the reference. Both will work fine. Now all we need to do is to use these references in each of the threads to pass the ownership. It will run fine. We saw how the same data can be accessed safely across multiple threads. But there can be a situation where we need to share as well as mutate the data within the thread. Suppose we have a counter and we want to increase the counter by 1 in first thread and increase by 2 in the second. To mutate, of course, we need to have the ownership. So we need to use the ARC smart pointer. But we can't really mutate this counter 1 and counter 2 because these are just smart pointers and doesn't support the binary operators. Also, you need to understand that when these threads run independently and simultaneously, both the threads will try to first read the variable when the value is 0 and then change it and finally write it. If thread 1 writes last, the counter will become 1, and if thread 2 writes last, then it will become 2. But in reality, what we expected was the value 1 plus 2 equals to 3. But we are not getting that. This is called race condition. To avoid this, Rust uses mutual exclusion or Mutex. So in this program, we can first import Mutex. Then inside the counter ARC, we can create a Mutex with initial value 0. Then before performing any operation, we first need to get a lock on the mutex using the lock method so that when this thread operates, other threads which wants to get the counter has to wait before this thread finishes the operation. This returns a mutex guard of I32. So to perform the increment, we need to dereference num and then use the operator. And also while printing, we can use the num variable. Notice we acquired the lock of the mutex at this line, but we never unlocked it for it to be used by other threads because in Rust, we don't need to. When this thread ends, Rust automatically unlocks the mutex. In other languages, for example, in C++, you need to manually write the unlock method. So if lock throws an exception or you forgot to write unlock, every other thread will wait forever, causing a deadlock. Rust completely eliminated this problem. Still, if we want, we can also release the lock by using the drop method. Now we can implement the same thing in the second thread, and in the print statement, we can get a lock on the counter to get the final value. Now this program will run fine. A limitation of Mutex is that even when a thread wants to just read the data and do not write anything, still it needs to lock the data, and other threads which also intends to only read it have to wait till this thread releases the lock. To resolve this, we have the read-write lock. Here, many threads can read the data simultaneously, but there can only be one thread to write at a time. In this example, we have imported the RwLock and used it similar to Mutex. Here, we created 4 clones of the counter, 2 for reading only and 2 for writing. We then have 4 threads. First 2 are same as before, increasing the counter by 1 and 2 respectively. However, instead of using lock method, we are just using the write method, which denotes that this is to acquire lock for writing. So when one of these thread operates, the other thread will wait for the write operation to get completed, and then it gets to write. The remaining 2 threads are only for reading the values. That's why it uses the read method. So it doesn't actually blocks other threads to wait. Whenever it executes, it will just read the counter with its value at that moment, and this will work just fine. So this is how we can read shared data without blocking any thread. Usually for this kind of operations, we use the thread safe types like atomic bool, atomic usize, atomic I32, etc. You can also use thread local macro to create thread local storage or TLS. These are exactly opposite of Mutex and read-write lock. It gives every single thread its own private copy of a variable. Threads never have to share, lock, or wait for each other. A common use could be keeping a local cache of database connections or expensive calculations inside each thread. By default, thread local data is immutable. To change it, you wrap the data in a container like cell for simple types like integers or ref cell for complex types like vectors or strings. In this example, we are using cell to create thread local variable. Inside threads, you cannot directly read or write these variables. You must use the with method with a closure as an argument. This safely lends you access inside the closure. So when you run this, you can see each of these threads have printed completely different values, though they are accessing the same variable. While exploring these, you may have a need to share data across threads. That may be sending a message from one thread which performs some critical section to another thread which may be responsible just for printing messages to the logs. In Rust, this happens using channels. Rust's strict rules make sharing variables across threads difficult. Channels solve this by passing the ownership of the data from one thread to another, preventing data races. In our program, we need to import the MPSC module. MPSC means multiple producers, single consumer. Now to create a channel, we need to use the channel method. This returns a tuple of a transmitter and a receiver. Here we are going to have two threads, so we'll clone this transmitter. Transmitters are going to be used by the producers. As we know that this channel supports multiple producers, so these two threads are going to produce and transmit messages through the channel. And in the main thread, we are going to consume all the messages using the receiver in a for loop and print them. If we run this program, it will print something like this. Instead of for loop, we can use the receive method with loop and match statements, where if we get a message, we print them. Once all the messages are received, we will break out of the loop using the error block. This would run fine as well. MPSC channel supports multiple producers, but it can only have a single consumer because it does not implement the clone trait, meaning you cannot copy it to pass to other threads. If you need to consume messages in multiple threads, you have two options. Either you use the receiver with Mutex and ARC smart pointer and get a lock on the receiver while using it. Or you can use some external trait which implements multiple producer, multiple consumer in true sense. A good example could be the Crossbeam trait, using which you can clone both sender and receiver freely in your program. In multithreading, thread safety is very important to have reliable execution of the program. For this, Rust uses two marker traits. One we have seen before, which is the send trait. If send is implemented by a type, it denotes that the ownership of those types can be transferred among threads safely. The other is the sync trait. This denotes that the reference of the types can be transferred safely. Most primitive types already implement these traits automatically. So that's pretty much all about multithreading in Rust. Multithreading is always a complex topic in programming, but vital in many modern design architectures. It is a great tool to have in your belt, but only if you practice enough. Let me give you an exercise. Write a normal program to create multiple text files using loop and write to those files. Then rewrite the same program again using multithreading and share your findings in the comments. Also, do let me know if you have any confusion in multithreading. I know it's a broad topic and there are a lot of methods to cover, but I'll leave it to you to try out. And I'll see you in the next one.